Thank you, Ben. Thank you very much for the kind introduction, and thank you very much that I'm having the ability, the possibility to be part of that amazing lineup of speakers today. Ben mentioned it, and you can see it here. I want to talk a little bit about metallic glasses. I'm not sure whether all of you have heard about metallic glasses. Usually when I have visitors in the lab, people, even if they have a background in metals, they don't know about metallic glasses or have only a very vague understanding of metallic glasses. So I want to actually spend the better part of the presentation to introduce you to those materials, showcase some of those nice properties, and also sprinkle in some of the extreme environments, not only in terms of temperature, but other extreme environments, and also sprinkle in a little bit of the nanotest. And as Ben mentioned, I'm the only thing between now and the lunch break, so I'm trying to make this as enjoyable as possible. Right, and as Ben also said, I'm now at Cranfield University, and not unlike the metallic glasses, people usually don't know what Cranfield University is or where it is. It's actually in the UK. It's a very small university in the middle of nowhere. It's somewhere, does it work? Oops. Oh, sorry. So it's in the north of London. Birmingham is somewhere here. We're in the middle between Oxford and Cambridge, and where the next bigger city is Milton Keynes, if you know that one. It's also not the nicest place. The special thing about Cranfield is that we are exclusively postgraduate university, so we only have masters and PhD students, and we pride ourselves with being the applied research powerhouse, tackling the real world problems, and we have close ties with industry, and many of our students' projects are actually funded by the industry. And of course, as with so many things these days, a lot of sustainability is going on, and including materials for sustainability, and metallic glasses somehow is part of that topic. And another specialty of Cranfield is that we have our own airport. So there are not too many universities in the world that do have this one, and you see that's in the middle of nowhere. There's nothing around here. And the history is that this came up from a Royal Air Force base in the Second World War, and still to date, we have a lot of research going on related to aerospace, materials for jet engines, and up to airport planning. And one of the biggest topic currently is hydrogen for aviation, for which we got a £69 million funding last year, and we are trying to work with that. Okay, without more ado, let's go to the materials, and let's dissect the term metallic glasses and start with glasses. We of course have heard about glasses in the previous two presentations, but I think when you think about glasses, you think about oxide glasses, right? So silicon dioxide, usually some more ingredients in there, and you may know that glasses are characterized by an amorphous atomic structure, but they are solid. So the amorphous structure, like you know from the liquid, but it's frozen into the solid material. So we don't have periodicity, and where the local order is somehow similar to that of a crystal. And as I said, you probably know this from window glass, or if you have glasses or a beaker or something like that. When you think about metals, you probably think about a crystalline order, in the ideal case nicely ordered in these crystalline lattices. But you may also, you probably know that it is never perfect. You have a lot of imperfections or weaknesses, if you like. You can have all sorts of lattice defects. You have grain boundaries. You have dislocations, and of course slip planes, and all these contribute to a lot of possibilities for plastic deformation. And let's now combine glasses and metals, and we end up with metallic glasses, and you may already anticipate that. So these materials are glasses in structure. They have an amorphous atomic structure, but they are composed of metallic elements. Mainly you can have some additives which are non-metallic, but mainly metals, and this provides these materials with a couple of unique properties I will highlight in the next couple of minutes. There's a subgroup of metallic glasses which are called bulk metallic glasses. Traditionally, these are metallic glasses which have a diameter, critical diameter, bigger than 1 millimeter. Nowadays, maybe more than 10 millimeter, and I will speak about why there's a size limitation in a few minutes. And also, these bulk metallic glasses are usually multi-component alloys, and not just any components. You usually select elements with many different atomic sizes. As I've sketched here, you see this is, I think, a 5-component model alloy, and you see these different colors also correspond to different sizes. And so the idea is to create a completely jammed structure, right? So you have maybe some big holes between the big atoms, and you fill this with smaller atoms, and the remaining holes you fill with even smaller atoms, and everything is completely jammed. So, and some key properties directly related to the structure are, of course, we don't have any conventional defects, which you know from metals. I've just highlighted in the previous slide. You have high elasticity, high yield strength, high resilience, high hardness, high wear resistance. And why is that? Of course, we can find out why is that if we compare this to the crystalline material. If you try to deform a crystalline metal, or you hit it with a hammer or whatnot, you can easily get plastic deformation, right? You have these slip planes. You can easily shear these planes across each other. You can create more grain boundaries. You can create all sorts of defects which eats up your energy and dissipates your energy into plastic deformation. In the metallic glass, as I said, everything is jammed. There are no slip planes, there are no defects, and so plastic deformation is not very easy to do, and also wear resistance, hardness would imply atoms to move somewhere, which is not easily possible in the jammed structure. There's also a high corrosion resistance because corrosion usually attacks at grain boundaries which extend to the surface of the material. If you don't have grains or grain boundaries, then corrosion has a hard time to attack these materials. And there's also a sustainability aspect, as I mentioned before. So if you have these nice properties in materials with relatively low melting points, then you would actually expect from materials with higher melting points. This gives you some advantage in terms of CO2 footprint when you make these materials. And the list actually can go on, but I have limited time today. And one question that usually or very often comes, are they transparent? No. Well, transparency has nothing to do with the term glass, right? So metallic glasses from the outside look like metals, but they share the very shiny and smooth surfaces with typical oxide glasses. So what you see here, this is something that comes directly from melting. You put your elements together, you want to melt in an arc melter, for example. You mix them properly, they solidify, and they come up with this nice shiny surface. Because you don't have grain boundaries that extend to the surface, and that makes the surface very smooth. Okay, a few of the mechanical properties here. Ultra-high mechanical strength. So I selected one of those diagrams. I had planned to show more, but I don't have enough time. So this is just showing the tensile strength over Young's modulus. And you see that the tensile strength is much higher compared to crystalline materials here. And what you may see, or maybe not, that the Young's modulus is actually usually smaller than that of crystalline materials. And in terms of the elastic properties, you have up to 2% elastic strain. Right, so imagine you have a rod 1 meter long of a metallic glass. You could extend this by 2 centimeters or compress by 2 centimeters, and it would go back to the original shape without any plastic deformation. And this can you nicely show here on the stress strain curve. There's a property called resilience, which is just the integral under the curve here. The Young's modulus is lower, that means the slope is lower, but the elastic limit is much higher, and that means that this area is much bigger, and this corresponds to the energy that can be stored elastically in a material. And this is bit abstract, so I brought you a little video here, which you may have seen, and I'm not sure if we can start that. Yeah. So this is just something very simple. There's a stainless steel column here, stainless steel base, and you drop a ball of stainless steel there, and not unexpectedly, where did the mouse go again? Right, this ball comes to rest quite quickly because all the energy is used for plastic deformation in the ball and the stainless steel on the bottom. If you take the same thing but put a disc of metallic glass on there and repeat the experiment, we get something like this. And this goes on for a while, and depending on the height of the ball, you drop, because the energy is stored elastically in that disc, no plastic deformation because everything is nicely jammed. Another experiment here, so I'm not sure whether you can see that nicely. You can buy ribbons of metallic glasses here commercially, and we cut off a little bit of a ribbon here and glued this on here. Right, you see this arc here is a side view, and what we can do is we can just push that ribbon, and you get this deformation from one arc to 3 and more arcs, and when you release load, it springs back to the original shape, and you can think of a lot of properties or a lot of applications you can do with that. Just for comparison, oops. The stainless steel, you get, of course, plastic deformation early on, and the stainless steel doesn't spring back into the original shape. If you want to play around with that yourself, I have a less sophisticated version here. You can just give it around. Okay, so just to highlight the nice elasticity of these materials. Right, oops. Yeah, some applications here. As I said, I just want to show you a little bit of pictures and videos. This is maybe an extreme application, not so much what I want to talk about later, but there are some things that also NASA is interested in using the high elasticity or high virus systems. Imagine you have some mechanisms in space, some space probes where it is cold, where you can't do maintenance. You need something with high virus systems and also high elastic properties. I'm not sure whether you know that a lot of energy is used in space probes to heat up the lubricant, right? Because the lubricant usually freezes. And if you can do without lubrication, then this is something nice to have. And here's another video showing the high elasticity. This is part of a so-called strain wave gear. I'm not sure whether you're familiar with that. I think they cooled it down to liquid nitrogen temperatures, and you see this nice elastic deformation without breaking this metallic glass piece there. And the idea is to apply this in different mechanisms there. There's another project by NASA called Cold Arm, as you see, for lunar exploration, where they want to use metallic glass pieces. And there are some more, let's say, mundane applications. I think the most famous one is the golf club. Right, there are some golf clubs where some pieces here on the bottom, that's the bottom, are made of metallic glasses. And remember the experiment with the ball. All the energy you drive in the ball is not dissipated into plastic deformation, but ends up in the ball, and you can drive your ball much further. And needless to say, that these golf clubs have been prohibited by many tournaments, of course. You have some other parts you can buy, some maybe scratch-resistant casings for different applications. There are some watchmakers that use metallic glass pieces. You may have seen these SIM card ejectors, sometimes are made of metallic glasses. And there are some applications in terms of medical things. And these are all coming from companies, so this is actually commercially available. Medical implants can be made from metallic glasses, And one of the main application, I think, is using those ribbons of metallic glasses, like the one you have in your hands, which is usually used as cores in power transformers to the soft magnetic properties of these materials. Yeah, a couple of more pictures of applications. You can do casting very small pieces to high precision, pressure sensors here to the high elastic properties. Again, there are some more consumer goods. Maybe you have some pieces of metallic glass in your cell phones. If you have a foldable cell phone, then you almost certain have a piece of metallic glass there because these hinges are made of metallic glasses. You can buy some headphones there. And there's another one here which is actually quite special. You can buy them. It's from a German company, and this is made by additive manufacturing of metallic glasses. If you like to spend £600 at this for this pair of headphones, please let me know if they really sound better. There's something else you can do with metallic glasses, which you cannot do with normal crystalline materials, and this is somehow comparable to the traditional oxide glasses. You can do blow molding, right? So you know blow molding probably with oxide glasses, and you can do the same thing with metallic glasses. You start with a simple rod-like thing, put it in a die, heat it up above a special temperature I will talk about in a second, and then you can form that, and then you let it cool down, and you end up with a nice shape there. And I think you can also imagine a lot of applications for that. You can also do injection molding like you would do with a plastic or a polymer, and this gives you the ability to come up with many pieces in a short amount of time with very interesting shapes, which are maybe hard to make for traditional crystalline metals, and you can come up with real functioning mechanisms made by those techniques. So now you may ask, if these metallic glasses have these wonderful properties, why is not everything made of metallic glasses or from metallic glasses, right? And the problem is how you make these metallic glasses. You need to be very quick. Right, so this is a simple diagram just showing the volume over the temperature of a liquid at high temperatures, and you cool down the liquid. Like, imagine you do a casting process, you start at high temperatures, you cool it down, and you know that in the usual case at some point the material just solidifies, crystallizes, and have this high jump in density, and you have a crystal and you lose all the nice properties. But if you do it correctly, or if you do it very quickly, you can considerably undercool your liquid way below the melting point of the liquid, and at some point the material turns into glass. We call this vitrification, and the temperature here is also called glass transition temperature. And in order to do this, you either need to be very quick, as I said, or you have a limitation in size. The smaller the piece is, the easier it is for the heat to get out, and this is where the size limitation comes in, which I mentioned right in the beginning. There are, of course, other routes of manufacturing. You can do this also in thin films in terms of coatings, or, as I said, additive manufacturing is a thing that is more and more in the coming. So, a little bit more theory. I will go through this very quickly. How to find actually materials which have a good glass forming ability, for which you have very low critical cooling rate, where you can cool very slowly and still end up in the glass phase. It's still very hard to predict these compositions, but we have a couple of empirical rules. The main one is to look at so-called eutectic points in phase diagrams, where you have low melting points in these materials, but you can understand that this is very hard when you look into materials which had 4, 5, 6 components. You cannot easily find eutectic compositions. Luckily, over the time, we have developed a lot of other empirical rules. Most important are the so-called Inouye rules, after Professor Akihisa Inouye in Japan. And the main rule is, as I said in the beginning, having a multi-component material, and you should have a significant size difference between these different elements, and yes, also would like to have some positive or some good attraction between those species. And these two rules combined is sometimes called confusion principle after Lindsay Greer. He mentioned that quite some years ago now. So if the material, if you have too many atomic sizes, the material doesn't really know what to do, which crystalline structures to adopt, and it just stays amorphous during cooling. This is the question: how many bulk metallic glasses are there? And I think this is a bit of an overlap to the high entropy alloys we have heard earlier. There are so many possibilities to put things in. It's hard to really determine what's there, but there's an estimate that that there are so many potential bulk metallic glasses which exceeds very much what we currently know, and there's probably a metallic glass for every application somewhere hidden in that big circle here. And of course it's very hard to test all of this, right? So by hand, and luckily we have nowadays possibilities like machine learning, artificial intelligence that may help us predict these compositions, or you can do high throughput testing, for example with combinatorial sputtering, where in a simple experiment at one time you can easily check many different compositions, and then you can select for the next steps you want to proceed there. Okay, so let me come to a particular application we are currently looking in, and I think there are a couple of other presentations in the afternoon. And this is now really the extreme environments part, nuclear fusion. Right, so actually nuclear fusion is a combination of many extreme conditions, and there was an idea early on in terms of metallic glasses that maybe there's an innate radiation tolerance due to the amorphous structure. Usually you think about neutrons disturbing or destroying the crystalline structure, turning the material into an amorphous material, but when you directly start with an amorphous material, that may give the material a high resistance against irradiation damage. And that was actually confirmed in many cases. In the beginning, when the idea was floated, there were not really bulk metallic glasses available, so the interest, I think, ceased a little bit, but only is growing now that we have the bulk metallic glasses, and there are also reports of possible self-healing of defects introduced by the radiation. And as I said, a couple of studies have been done, and this is a bit of a review here from some colleagues. And usually this is done by off-the-shelf metallic glasses, using known compositions, and people had some radiation source available and they just put it in there and looked what's going to happen. Sometimes you get crystallization, sometimes you don't, but there's no really systematic study done there yet, and I think this is something we want to look into the future. There are also some other beneficial properties in terms of nuclear fusion in relation to metallic glasses. When you think of hydrogen retention properties, there's some problem with hydrogen or helium in the structure forming bubbles and whatnot. And this is very often related to typical crystalline defects. But if you don't have those crystalline traditional defects in metallic glasses, that might be very beneficial there. The corrosion resistance, as I mentioned at the beginning, is a very big part. You may know that there's a lot of discussion in using molten salts or liquid lithium in nuclear fusion, and this may be beneficial there as well. And yeah, the variety of possible applications which you can think of, and as I mentioned, there's no dedicated development yet. And one big aspect is, and I think probably Thomas or James will talk about this in the afternoon, there's something called activation. Neutrons can transmute elements in the material into radioactive elements, and you want to exclude these elements in your alloy composition. But the problem is this is a contradiction sometimes to the glass forming ability, right? I mentioned earlier that we have some empirical rules knowing which materials give us a good glass forming ability, And the problem is that many of these elements are prone to transmutation into activated nuclides. And so you probably somehow need to restart your design thinking of metallic glasses from the scratch and see what elements are possible and how can we still get high class vulnerability. And we have written a little review there to highlight all the possible applications of metallic glasses in fusion. One of the promising materials are high temperature metallic glasses based on refractory elements. They're especially tungsten based, and we are working on this. We have some preliminary results. Sorry, I can't go into more detail due to IP things there, but we have some materials with glass forming temperatures way above 1000 Kelvin, on crystallization temperatures above 1200 Kelvin. And also these materials show extremely high hardnesses there, which are, for a metallic material, quite high. And this is something we have done, actually Ben has done, and I was looking while he was doing this. And and I think there's more to come. And sorry that I can't go too much into detail here. Yeah, so that was also a bit of a whistle-stop tour. I hope I could show you that metallic glasses are outstanding materials with amazing properties which allow for many applications in different fields, and we hope that nuclear fusion is one of those fields in the future. And of course, a lot of research is going to be needed in order to confirm this hypothesis. Metallic glasses for other extreme conditions, high temperature and so on, is an emerging field, also away from nuclear fusion. And there's something I didn't talk about today due to time limitations, and I think there in situ tests are needed, and we are hoping to have the new nanotest advantage in Cranfield soon, and maybe also have the possibility to measure at high temperatures. All right, then, thank you very much for listening.